The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Today on The New Quantum Era, we're interviewing Martin Savage, who is a professor of nuclear theory and quantum informatics at the University of Washington. He runs a research team there, exploring how quantum computing systems can investigate subjects in high-energy physics and quantum chromodynamics. He also runs the incubator at the University of Washington on quantum simulation. Interesting guy.
Yeah, really interesting, Kevin. I met Martin where he gave a talk actually at a workshop at University of Washington that I attended earlier this year, where he highlighted the results that are published on a paper on the archive titled Quantum Simulations of Hadron Dynamics in the Schwinger Model using 112 qubits. And it was kind of breathtaking, actually, because it's the scale of the experiment. He used the IBM's Heron chip, which is 133 qubits. Used most of those qubits, where most experiments on quantum computers these days tend to be in the sort of under 10 qubit kind of range on average.
Yeah.
Right, exactly. So used over 100 qubits and really a staggering circuit depth and length of job. So it was one of these really rare instances where the work had scientific merit in and of itself and also pushed the limit of what you can do on quantum computers today. So I immediately said, ooh, we need to have him on the podcast to learn more.
Good stuff. I think it's going to be good.
Welcome back to the podcast. We're joined today by Dr. Martin J. Savage from the University of Washington, professor of physics, also the PI for the Incubator for Quantum Simulation, which is a really fascinating center that's hosted up at University of Washington. And welcome, Dr. Savage. How are you?
Yeah, good. Thank you very much for hosting me.
Welcome on, man. Yeah.
Very glad to have you with us. So if you don't mind, we'd love to hear just a bit of your journey to quantum computing. You're in nuclear physics, I believe, right? And you sort of
That's
jumped
right.
more recently into quantum computing.
Yeah. So I made the transition around about 2017, 2018, and it coincided with a few things lining up. But I thought I'd tell you roughly where I came from and then how we got here, if that's okay.
Awesome. Yeah.
So I did my undergraduate work in Auckland, New Zealand. And my master's thesis was in experimental nuclear physics. They had an accelerator there, and it was a great education. And then I came to do my PhD at Caltech, and I started as a nuclear experimentalist and switched into theoretical particle physics. So my advisor was Mark Wise. We worked on beam meson decays, and this was starting in the mid 1980s. I was there 85 to 90 at Caltech, and Feynman was giving lectures on quantum computing at that time,
right.
But I didn't pay much attention. It seemed a little exotic, and I was really focused on and Murray Gilman was giving lectures on IGUSs and information also. I took that class, and I found it fascinating. And Seth Lloyd was there as a postdoc at the time. So that was the beginning, but I really didn't engage and pay attention. I was focused on high energy theory. And so then I was a postdoc at Rutgers University and a postdoc at UC San Diego, and we were working on sort of low energy effective theories for strongly interacting systems. And then I was assistant professor at Carnegie Mellon University in particle theory. And then University of Washington came along and said, would you like to return to nuclear physics? And so in 1996, I said, yeah, gladly. And I came to UW. I was a nuclear theorists working on effective field theories. And then we got to this point in developing these theories where we realized that in order to really go further and get the precision we needed to have impact, we had to go to large-scale numerical simulation. And so I switched at that point with, two or three others. We formed the NPL QCD, Lattice QCD collaboration. So it was nuclear physics with Lattice QCD. And largely against the advice of all of our colleagues and friends, we put in significant effort to compute strong interaction processes using Lattice QCD, multi-nucleon and nuclei. And we made really good progress. And so then I was involved in the exascale process and evaluating the resources required for nuclear physics to get to where we needed to go. And so this was around 2017. And we realized there was classes of problems that exascale and even beyond exascale we're just not going to get to.
Right.
And these were problems that were finite densities of fermions and also dynamics. And so there was a sort of moment in that period where it's like, okay, we need to do something else here. And it was also at that moment that IBM's devices were coming online. So those two things lined up well. And so we said, okay, can we do this? And that was pretty much the beginning of the transition, at least for me.
That's
and
so interesting.
For others.
Before we get into the quantum computing part, I'm just curious, the idea to use numerical simulation for particle physics, nuclear physics, was there any sort of inspiration or borrowing of techniques from computational chemistry in that, or what was the impetus around that?
So great question. I mean, from the high energy physics point of view, large scale simulations have been going on at least at the fundamental level since the early 1970s with Lattice QCD. So this was Wilson, Kreutz, and others that really, laid down the foundation very shortly after the formulation of QCD itself. And there's been, through that evolution, an interchange of techniques between fields, right? So one way quantum field theory is a little peculiar because it really is dealing really complex numbers are critical. The I in I squared equals -1 is really central to what we do.
Doubtless.
And so the techniques are similar, and there's been a lot of sharing, quantum chemistry, quantum many-body systems, condensed matter systems, and high energy physics and nuclear physics.
Right.
And that's continuing and sort of accelerating even a little bit on the quantum side.
Right, right. I mean, that's sort of where I was wondering if there was a connection, because computational chemistry is also finding these sort of bottlenecks and blockers where even exascale and beyond methods are not going to yield results. And quantum computation actually has a potential path forward if we can improve the hardware fast enough.
Yeah, that's right. So dynamics is one area which is sort of globally one of these global areas where quantum computing is going to make the difference. It's going to be the only path forward to get to some of the things we got to get to.
We've heard that same theme in past interviews, right? Is that for many people who are, the cutting edge of science, the very issue of dynamics is wildly challenging in terms of classical numerical methods. There's really almost no other way forward besides quantum computing. Is that a fair characterization in your mind?
Yeah. I mean, you're really, from the techniques that we have to use classical computing, we're really stuck. They just don't take us to where we need to get to.
Right. So that makes you a pretty early adopter of quantum computing. I mean, IBM System on the Cloud is about the first chance most people ever got to get their hands on, virtually their hands on a quantum computer. So you've been doing this now for close to 7 years or something. That actually makes it gives me more context for the simulation that I saw you describe at the workshop at University of Washington, which I guess was this past December, right? It was quite a huge step forward from what I've seen with other similar efforts.
Yeah. So the original calculation where we were actually brought in by people at Oak Ridge. So we formed a team at Oak Ridge in 2017, and the first calculation that they did a calculation looking at the ground state of the deuteron And the work that we were involved in here at the University of Washington was actually the Schwinger model on 4 qubits. And this was a natural place to go. The Innsbruck team on 4 qubits of trapped ion systems had done the first calculation, and that was basically, the light turned on and it's okay, this is where we got to go.
Right.
And the work that we did in December, so there's been a long path, right? And so we sort of roughly have pretty good idea where we need to get to, but it's a case of somewhat a mercenary approach, like, okay, we can do this now. Okay, we can now do this. Okay, this is where we're going to go. And we did a calculation in August where we built on some algorithms that had been recently developed and developed scalable algorithms. So our problems have a lot of symmetry. They're basically discretely translationally invariant. And we came up with circuits in such a way that you could actually tune them up on modest-sized classical computers and then scale them out to arbitrarily large on a quantum computer. And so we demonstrated that to prepare the quantum vacuum of the Schwinger model. And then what we did in late December, and I'll come back to one particular point, was to then start doing dynamics. So we created a lump of energy, and then we could time evolve it forward for a significant number of time steps, and then watch these composite particles form and then propagate out. So we saw a light cone of composite particles in this system, which is very much on the path of where we want to go for strong interactions in quantum chromodynamics. So the size of the system, the simulation we did was 112 qubits, and we ran 14 time steps, and that largest one required 14,000 CNOT gates and a depth of 370. Right. So it was a beast. It was a beast of a calculation.
Yeah, no kidding. I mean, the IBM 100 by 100 challenge was just issued, I think, earlier last year, maybe in the spring, where when they released that system that you ran on the Heron 132 qubit chip, they were calling for somebody to try running a 100 qubit circuit, or a circuit using 100 qubits with 100 circuit depth, and you blew the doors off that with your first attempt. That's impressive. How did you manage to run that many CNOT gates?
Quite easily, it turns out. Well, no, I'm being facetious. So the part of the key here was, firstly, the error mitigation that we used. It was a variant in what had been used before, and it turned out to work very well here. But also the fact that our system again has this translational invariance, and so there's there's similarity in the correlations as you step from plus infinity to minus infinity, and so that helps enormously. So it's very much not an arbitrary quantum circuit. It's a very structured quantum circuit. So that helps significantly in being able to do this. And so, we ran 150 million shots. And applied. It was a significant resource. And what made this possible was, in fact, that we've all run on large scale compute systems, and they always go pretty quiet between Christmas and New Year's, and we were ready. And so that's what happened.
That's really funny.
So that's really interesting. So the decoherence issues and maybe the errors on gates themselves, you largely able to surmount that by the symmetry of the problem, and perhaps that the amount of runtime required was just minimal relative to the result objective.
Yeah. So we constructed the circuits had a lot of periodicity to them. They're translationally invariant by 1 unit each time, and so when you stack the circuits on top of each other to implement one layer in the adapt VQE algorithm, then in fact you could do a lot of cancellation and there's a lot of compression. So the first layer was as dense as it could be. The second layer was very dense. It wasn't perfectly dense, but it was very dense, and so there was a lot of compression that happened. And so the 14,000 CNOT gates compressed down to 370.
Right.
And so that's sort of where some of the magic was that happened here. Yeah.
And
if we'd have had to stack them out arbitrary deep, it would have just not worked.
Right.
It would have been a total failure.
And did I hear you correctly? So this is essentially a VQE algorithm at its core.
So yes and no. So we use the VQE algorithm, the adapt VQE algorithm, to build the operator structure using classical computers. So we tuned up that circuit because it's localized. We could actually tune it up on a classical computer and get these angles to be exponentially close to where they needed to be. And so once you have those angles, then because we'd set up operator structures that could be extended to arbitrarily large without changing those angles, then we're able to actually blow out the entire quantum register, but without having to do an iterative VQE on the quantum
Interesting.
computer.
Because of the circuit scaled up, the right.
Yeah.
That's right. Okay. Got it.
Yeah.
So once you got a good approximation on the classical VQE simulation, you were able to apply that to the scaled up circuit on the entire. That's
Absolutely.
really cool.
Absolutely. Yeah, it's again because these theories are confining. So when you look at how charges correlate as you move them apart, then once you're outside a few confinement lengths, then all the correlations drop to zero exponentially. And so you really only have to worry about a small volume and get that right. And you can do that with exponential precision. And that's what you do on the classical computer. That's where the VQE part is. And you can do that classically. That'll change as you start going towards a continuum. You'll have to then you can then tune up on a smaller quantum computer to scale to a bigger one, but you're still having this great simplification.
So it's a problem ideally suited to the current era of QC.
Yeah. So I agree exactly. I think that there's a chance that these one-dimensional systems, which is where we're looking at now, these if you perform scattering, so I take two clumps of energy and I collide them together, computing what happens is beyond classical computation, but it could be that within a reasonable period of time, like 2 years, you could actually do that on a quantum computer with today's quantum computers. I think it's close.
That's amazing. And am I right in thinking, I mean, you just described as two clumps of energy colliding. So that's the type of work that normally experimentalists do in, say, the Large Hadron Collider, for example, right?
Exactly, yeah.
So you're replacing this enormous piece of lab equipment that's buried under the ground underneath Geneva with something that can fit in a Dill fridge in a data center.
I would never say that.
Fair enough.
No.
but perhaps one day you have hopes.
So one of the things if we look at study how lattice QCDs evolved, so quantum simulations are comparable to where lattice QCD on classical computing was in the early 1970s. I mean, right around its creation, and in fact, the classical computers then were a little bit more capable. So there was a lot development period, and it's only recently, I would say in the last 10 years, that the lattice QCD simulations have been able to provide results that are better than what can be obtained from experiment. But there's classes of things that are better. I mean, we're learning things about, weak interactions because we can do strong interactions factors of 3, 4, 5 better than you can do from experiment. But replacing experiment, I think, is not the right way to think about it. It's supplementing and complementing. Right. That's how I view these things.
Right.
And guiding future ones.
Bad choice of words on my part. I meant in this particular experiment, you were accomplishing something that otherwise you would have needed to try to simulate or to do experimentally with some large piece of work.
Yeah. I mean, it's very much a complementary and supplementary activity. It's not a replacement.
So totally understand, but still, I mean, it's a provocative line of inquiries, and to sort of at least try to compare what you're currently doing with, say, the past history, the long 100-year history, right, of colliders, accelerators, etc.
Yeah.
I mean, is that a fair comparison? And if so, I mean, what era of experimental technology have we reached by simulation in a QC, do you think?
Yeah, so this is a great question, right? And so on the QCD side of thing, and where we're aiming for, with the quantum simulations area, is to be able to you basically verified the technology and proved that your numerical simulations work with high precision. You can make predictions, which then you do experiments and they're borne out. And then you can take the simulations and go to environments where you can't do the experiment, like in the core of a neutron star. Wow. Or when right. And so it's to go to places that you can't go,
right,
either through observation or terrestrially. That's the objective. But, the experiment, you need to do the verification stage, and that's critical to be able to make sure you have your errors right and you can make predictions. Yeah.
Is that something that work, the theoretical work is sort of underway, where the community is starting to build kind of a model for what the interior of a neutron star might be, so that you can actually perform experiments in that theoretical context?
Well, yeah, there's a lot of effort to try and do that. I mean, these are remarkably complicated environments, and well, yeah,
sounds like it.
and so, for instance, when a supernova collapses, enormous energy is released, and you need to understand what's there, but you also get a large production of, for instance, neutrinos. And neutrinos have long wavelengths associated with them, and they can change their flavor, and they can interact with each other. And that's something, again, that's again a beyond exascale challenge. That's something, so people are looking to simulate the dynamics of neutrinos coherently scattering with each other, which is fundamentally quantum mechanical, is to try and get a better handle on what's going on in those extreme environments. Really so that's something else that's also being done in parallel to what we're doing. Yeah.
I sometimes have a habit of asking our guests to a little bit speculate on the future here. But I mean, I'm trying to maybe brainstorm with you a little bit. Permission, please. But there are numerous theories in physics that are, deep in the range of theory that many people criticize as being essentially untestable, given just the amount of power and energy available, in just the solar system, right? It's just there's so much extreme energy is required. But could it be the case that perhaps some of these techniques could push the boundary, right, of computation-based experiment in ways that could test at the limit some of these rather out there theoretical projections?
Yeah, absolutely. I mean, it's when quantum simulations get to the point where, they take you beyond classical, you're going to be able to probe ideas in environments that you just can't do any other way.
Right. Wow. Yeah.
So some of the theories, I think, will remain beyond the boundaries, but
beyond civilization. Yeah.
But it's definitely going to help in pushing that type of research forward. Yeah.
Really interesting. And can you perhaps bottom line that some more? I mean, what are the major large theories of everything do you think perhaps could be probed successfully with these methods?
Yeah, no, I mean, I think I'm not going to venture down that pathway right now. It's setting myself up for but I appreciate the question.
And so I mentioned the incubator for quantum simulation, which I guess that's NSF funded, right? The primarily.
No, it's actually DOE funded through the Office of Nuclear Physics through Quantize. Yeah,
right. That makes sense. Yeah, and so this would be the work that you've done is sort of fits obviously under that umbrella. Are there other areas within? You actually bring quite a disparate group together in that incubator, and they sort of have quite a creative kind of mixing, don't they?
Yeah, absolutely. So the incubator's got really sort of three different functions. So we have the local research is one of them. Another important component is the workshops we run. So I took a leave from the Institute for Nuclear Theory, where I was a member there for a long time. And we work together. So the incubator holds 1 month a year of programs. So basically two-week programs. And we bring together people from all the different areas and particular focus topics. And so from quantum, engineering, people from tech companies, universities, national labs, to focus on something that would benefit from having people sit here and talk to each other and present for an extended period of time, and we hold those in the Institute for Nuclear Theory. And they're very lightweight. It's a think tank environment, excuse me, and all of them have been, really, I don't want to say surprisingly successful. They're working as we'd hoped, but they've really been special in the sense that after somebody in the elevator said, one of the attendees said, we arrived as fermions and left as bosons, because the first week people from different areas don't quite know each other's language, and they've not met each other before sometimes, and then it takes about a week, and then in the second week people it starts gelling, and it's really exciting to see. Yeah.
Do you think that in a sense the quantum information science is almost acting as a lingua franca that's sort of crossing the boundaries between these different disciplines within physics and other physical sciences?
It's absolutely it's starting to. That's right. Huh. So this is something that's new. Sort of where it is today, it's sort of new in high energy physics, new in nuclear physics, new in the domain sciences to some extent. And some of the ideas and concepts have been in the fields, but they haven't been sort of formalized and put together. But now with quantum information now becoming, prominent and recognized as central to making advances in these areas, it's really starting to come together like that. And the concepts of information that are now coming into high energy and nuclear physics are actually changing how we think and allowing us to do things that we wouldn't have been able to do before. I mean, it's really making a difference. And then also conversely, and this is kind of also part of the point of the workshops, is that we have technology, for instance, in nuclear physics, the nuclear many-body technology. So some of the nuclear models that have been studied since the 1960s are also, for instance, have Hamiltonians that are used for spin squeezing on programmable quantum sensors, as example. So we have a lot of technology we developed for specialized problems that have more general applicability, and that's now also being dispersed within the communities. Wow. That was just one example. Yeah, so there's really an increasing exchange of information and ideas that's really beneficial to everybody in the advancement of multiple fields.
Multiple fields, yeah, it's so exciting.
Yeah, it does seem perhaps indicative of a trend where more and more it's the case that quantum information sciences become sort of core to pedagogy for students of high energy physics and similar, huh?
I think it's going to become one of the themes that allows you to understand not only what you understand experimentally, but how you understand how the theories are working and how to make advances in problems that were, I don't want to say too challenging, but where progress has been slow. Yeah. I mean, this is bringing in new ideas and new concepts. Absolutely. Wow.
Yeah. So
it's really an exciting time. I mean, really exciting time.
It really is.
Yeah, in many ways. We live in miraculous times.
Yeah. It is remarkable every time I think about how on the nose Feynman was in 1981 with that keynote. If you could only see where we come to now, it's pretty extraordinary progress for that amount of time. So when you look ahead, Martin, just as a maybe a wrap up question, do you have sort of targets in your mind or accomplishments that you're sort of working towards that you can share? Because obviously you don't want somebody to scoop your your research results, but
absolutely. I mean, at least in nuclear and high energy physics, there's a number of sort of large scale objectives. They're all, the ones we're sort of focusing on at the moment are sort of these non-equilibrium questions of what is the nature of matter under quite extreme conditions, and when you tries to compress it or heat it rapidly, what does it do? And we don't know how to answer these questions really. For me, we are sort of chasing how to do QCD and strong interaction physics, the dynamics at high energies. I'd say that sort of captured it. So what we talked about before. Mm-hmm. If we could start from, say, two very high energy protons, collide them together into these large showers that you see in the colliders, we can make progress towards and making postdictions and then making predictions. I mean, that would be phenomenal.
Yeah, really amazing.
Wow, and at least in 1D, I think we're making some progress. 2D and 3D is harder, but 1D is we're learning a lot and we're making progress. So Yeah.
Well, there's no other way to characterize the result from that paper that you released, I guess, in early January, other than progress. I mean, that was a huge step forward in terms of an actual result. So my hat is off to you. It was really quite impressive.
Well, these things were made possible by having, great teams.
Of course.
I have to mention, there's great postdocs and students and junior faculty here that are contributing, all in very special ways. So that work was made possible by good teamwork, having good collaborators.
Fantastic.
For sure.
Great spirit. Yeah, good stuff.
Awesome.
We're so grateful for your time, Dr. Savage. Thank you.
Oh, thank you very much. It was a pleasure.
That's great.
Wow, another fascinating interview. I love these conversations with people in the sciences using quantum computers, right, to explore actual frontier questions in the higher sciences. I mean, just amazing stuff. This is probably one of the biggest frontiers where there's actual real applicability, right, of and value for a high volume quantum computer setup. So just amazing stuff they're doing on that team.
Absolutely. We've said it before, but this really is the culmination of Feynman's vision from that keynote in 1981, right? I mean, these are Feynman machines. We're now getting to the point where we're simulating quantum systems that you can't otherwise simulate in classical settings.
Yeah, and he really just laid it out plain. It's like essentially for any of these computational problems that he's dealing with, there's no way
right.
a classical computer could get on top of this question.
Right.
So it's just
and super. I mean, you asked some probing questions there, Kevin, that Martin didn't want to make a committed answer to for obvious reasons.
I thought the question was really. I hope he didn't get pissed off by that one. Yeah.
No, I'm sure he didn't. I mean, the implications of what he's talking about is if there is a path forward with quantum computers that extends the computational approach to high energy physics, that community is going to start to be able to do things that otherwise would be, need a huge amount of investment, capital investment in a collider or an accelerator, or potentially wouldn't even be possible in those settings, right?
Yeah, you could do in code what only could be done on a cyclotron. So kind of cool, right?
Right. Well, and you went even further and asked him, are there any particular, areas where you think there might be, progress towards like a theory of everything kind of?
Well, or at least being able to run some of the experiments that are needed to, falsify or endorse, right? Some of these theories of everything that require just, absurdly fantastic energies beyond any hope of realization as a real world experiment. So it's kind of cool. Right. And of course, he politely stepped back from speculating on this one, but I did have to ask.
Of course, you got to be the rabble rouser. I thought it was also really notable. Some really interesting characteristics that were specific to Martin's workload here or use case. One, it touches on one of our themes for this year, which is we're sort of questioning whether there is any value that's going to be realized from variational techniques, VQE in particular, sort of being pronounced dead in 2023. In one sense, this is another, a lifeline for VQE because he actually did use VQE in a classical setting before running the experiment on the actual quantum computing system, which I thought was really interesting.
Yeah, really interesting. Yeah. But just an amazing tour de force of his entire team. And it was just great to hear him acknowledge it was a gigantic suite of talent required to produce this result. Yeah. So
absolutely.
Just fascinating science, really.
Yep, absolutely. And I think, there's certainly more to come from that group. And I'm also looking forward to seeing how these sorts of, he sort of referred to the techniques and the technologies that the higher energy physics and particle physics and other subdomains of physics are developing and sharing among one another. And I think that's, we're going to see acceleration almost, necessarily out of these types of efforts across the board.
Yeah. And in closing, it was really thrilling for me to hear how he's acknowledging openly, right, that the pedagogy in higher energy physics and these subjects, necessarily will more and more have to embrace, programs of quantum information sciences in order to fully, realize the possibilities of the current era. So just great insights. Very, very enjoyable.
It really was. All right.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.